Greetings. In this one, we'll look at groups of units. These are kind of related to the groups integers modulo n in the way that we can actually derive the elements that belong to a group of units by knowing what integers modulo n are about. And I would highly recommend to first know far before looking at group of units to know well integers modulo n, because there's some things to consider while working with group of units, that there is an implicit way. We'll now look at it to look for their elements directly through integers modulo n. And so first of all, I'll quickly introduce integers modulo n, but just really briefly. Perhaps it won't be enough to get a grasp of it just from this quick intro. So groups integers modulo n in general, they go like this. They start with 0, go 1 through all the way until n minus 1. So they go 1 by 1, 0 through n minus 1. These are the elements that belong to n. And with them is associated, for example, integers modulo n with multiplication. But what is meant by it is actually modular arithmetic. And that means that if we take some elements a, b, inside this group, then the result a times b will be a times b, but it must be via modulo n. And via modulo n means that you divide by n and then take the remainder. So whatever the index for this integers modulo n is, that determines 0 through n minus 1, the list of the elements first of all. And second of all, it also determines the modular arithmetic. The entire idea is basically when one does modular arithmetic with n, one divides by n and looks for the remainder after division by n. That means 12 mod 3 will be 0 because 3 fully divides 12. But 11 mod 3 will be 2 because 3 fits there 3 times and then 2 is left as a remainder. So when we look for some numbers, for example 2 times 5 mod 3, it won't be 10 because it has to have mod 3 applied. Often put it in parentheses like this. That means divide by 3 and get the remainder. So 2 times 5 in modular arithmetic with mod 3 is actually just 1. And this is a thing that is applied directly in integers modulo n. And so let's now look at groups of units n, because they also have this index. So group of units n is like u with subindex n right here. And let's first of all look at some ways to get their elements. So for a group, of course, there's some operation assigned and so on. Later I'll show that as far as abstract algebra, just like integers modulo n, they also form a group under multiplication modulo n. But let's look at how to look for their elements. There's more ways. There's an explicit way that I'll show in a second. And now let's look at the implicit way, which is directly related to integers modulo n, because integers modulo n are 0 through n minus 1. And we can have under multiplication it closed with the modular arithmetic. That means whatever two elements from integers modulo n we take via modulo n modular arithmetic with mod n, the results again fall into the set of elements that belong to that integer modulo n particularly. So it's closed under this modular multiplication. And this will also fulfill it, but let's look at how to get the elements of a particular group of units n via the knowledge of integers modulo n. So there is something called a unit, and this is also the reason for the name. So with integers modulo n, we know that we are going to get different numbers after multiplication of well-known numbers than we would expect via usual arithmetic. For example, let's look at the example of integers modulo 5. We know that to them belong these 5 numbers, and the multiplication is defined in the way that there's 2 numbers that belong to this group, and a times b, yes, are multiplied, but if we call this the multiplication alongside with the knowledge of the modular arithmetic, then it means usual multiplication, but we apply the mod n. And in this case, because it's integers modulo 5, it's mod 5. That means that we take 2 numbers here, we multiply them, get the result, but then take the result as the remainder after division of it by 5. That means that if we, for example, to take 3 times 4, well, 3 times 4, we have to do mod 5 after that. So it's not 12, but it will be 2. Because 12 divided by 5, the remainder is 2. So that's the idea for integers modulo 5. And let's look at how to find, now finally that we know this fact that we can have different remainders. And for the, by the way, for the integers modulo 5, we can have an example where we have 3 times 2. And what is that? Initial calculation at 6, but with modulo 5, that's 1. And this is called a unit. When the result is 1, it's called unit. And we're looking for numbers that fulfill this requirement, that fulfill this solution, this result here. And when we look for these numbers, these will directly be members of the group of units n. So when we have integers modulo n, via that, looking for numbers in integers modulo n that in product, after the modular arithmetic is afterwards applied, give 1 as a result, those are members of group of units with the same index n. So we're always talking about numbers 1 through n minus 1 that can be elements of un. The group of units n. So let's do it with integers modulo 5. Let's try to look for elements of group of units 5. That means that we will again use the integers modulo 5. I can list the elements once again. And what I want to look for is AB in integers modulo 5 such that A times B equals 1. But here it's of course mod n, so in this case it's mod 5, as we had experimented with before. So we're looking for numbers inside integers modulo 5 such that if we multiply them together, after modular arithmetic of mod 5, they give 1. We already know that was 2 and 3, because 2 times 3 is 1. And we always talk in mod 5 in this case. You know, I'm writing it shortly. I could have written mod 5 in the parentheses just to denote it explicitly, but let's be quicker. Also, I can take elements and put them in operation with themselves. So 1 will satisfy. 1 times 1, mod 5 is 1. So it's also satisfied. Another thing is 4 times 4, we have 16. Mod 5 is 1, the remainder is 1. So here what we're doing is we're looking for operations on these elements. There is multiplication such that the remainder is 1. The remainder of that number is 1 after dividing by, in this case, 5. So group of units 5 is these numbers that led to the result 1 after the modular arithmetic application. So it was all the 1, 2, 3, 4. In this case, a lot of numbers fulfill it. And especially in these lower index numbers, there are a big proportion of the numbers are like this. In higher numbers, not necessarily, 80% of the numbers are of the possible numbers that belongs to, here actually 100 of the possible numbers, because we're always looking at 1 until n minus 1, which in this case it was exactly these ones. Let's look at some other example, but let's look at another way to look for the elements of the group of units, because this is not the only way, and via some analytical looking at it, although now we're kind of playing with numbers and looking for them by eye, we're not really going deep into the theory how one can perhaps find some techniques to quicker find these factors and so on. That might slow it down, but we're doing smaller numbers, so it's kind of quick to do by eye and by trial and error. So let's look at some other example, and let's look at the more explicit way to yield the elements of the group of units without knowledge of the parallel integers modulo n. So we're doing group of units n, but let's look at for the elements of it without using integers modulo n. So let's do group of units 12, for example. What will it be? Well, another way to look at it is that we are looking for the numbers that the elements will all be represented by a. Why? It's because here I'm talking about a in this expression, and it's always n and a together. Their greatest common denominator is 1. That means that the greatest number, the highest number that divides both of these numbers is 1. In other words, these two numbers are co-prime, and the n is this 12 here. So n is the index of the group of units, and a are the individual elements. So the elements of a group of units are all the numbers that are co-prime to the index, to whatever the group of units is associated as an index with. Group of units 5, all numbers co-prime to 5. As simple as that. So let's look at it. Let's look at what numbers are co-prime to 12 in this case. Well, 1 is, then 2 is not. We have to be careful not to pick numbers that are not 1 but divide, not to, for example, look for numbers that, so 1 is the first example. Another example is 3. 2 it won't be because 2 divides 12. And actually 3 it won't be also, that's mistake, because 3 also divides 12. Another number will be 5 that does not divide 12, and the highest common denominator of 12 and 5 is 1, which satisfies the requirement we had here, the identity. Then 6, well, 6 divides 12, therefore cannot be, and even then there will be higher common denominators, for example 2 and 3 for both 12 and 6 together. Then 7 will work out because 7 doesn't, the greatest common denominator is 1 and 7 does not divide 12. Then 9 cannot work, 8 cannot work because there's bigger greatest common denominators. 9, also 10 the same, and 11 will work. The greatest common denominator is 1, and neither does 11 divide 12, of course. So these 4 numbers are the only members, the only elements of group of units of 12. We can also verify it via looking at the integers modulo n and seeing that these numbers are in products the ones that will yield 1 when put in multiplication. We can try it out. So it contains a lot. We can look at it, so we can try it out. First of all, what we want is that we take these elements, somehow we put them in product, and we want the remainder to be 1 after we divide by, in this case, 12. So 1 to the second power, for example, by itself, yes, that will be remainder 1. 5, we can put it to the second power, which is 25, mod 12, yes, that's 1. 7 to the second power is 49, and yes, this directly is 48, so the remainder is also 1. And 11, well, we can try 11 to the second power actually, mod 12 will be 121, and 12 fixed 10 times, and then 1 is the remainder. So yes, this is 1 as well. So all these numbers satisfy 1 satisfied because it's just 1. For example, 1 to the second power is exactly what we wanted. Otherwise, if we multiply 1 by these other numbers, then 5 mod 12 will be still 5, 7 mod 12 still 7, 11 mod 12 still 11. So it's not that all of these numbers with the other ones with any will together create the situation that the remainder after division by 12 of the product will be 1. It's that, for example, it with itself will at the second power then as divided by 12 give a remainder of 1. So here is the usage of knowledge that basically the elements of a group of units is numbers 1 through n minus 1, so in this case 1 through 11, which of those numbers are co-prime to 12. And then these numbers are the elements of the group units U12. Now what we can do is we can also verify that indeed these group of units n, they are actually in abstract algebra sense groups under multiplication mod n. And why? Well, a way to verify, well, we could look for inverses, we can look for identity and so on. Where for multiplication the identity of course is 1, which is contained. But let's look at, for example, at this example again, and let's verify that it is closed. So we know, and we could prove it lengthily, we won't go into it right now, but we know that groups of units n, under modulo n, under multiplication form groups. So we know that if we take these numbers and put them together in multiplication, the remainder after division by 12 again will be one of these numbers. So we can take some examples. 5 times 7 mod 12. What will it be? It's 35 mod 12, and that is 11. or we can take 7 times 11. 7 times 11 mod. I'm just taking random one just to show that whatever ones we take, it will satisfy what it should satisfy. 77 divided by 12, that will be 6, and then remainder will be 5. So 5, and again we see 11 belongs back, 5 belongs back. In both cases, these both, and it was a third number of the 4. That was actually the modular result here. 7 times 11, and again, third of the ones. We could do 7 times 1 straight away. It's smaller than 12, so straight away it's 7. 1 times 5, yes, it's 5 straight away. 1 times 11, 11 straight away. 55, you can try it, 55 mod 12, because that's 5 times 11 mod 12. So we have 48, and then remainder is 7, so it's 7. So we see that indeed it also gets satisfied, and groups of units under multiplication mod n form groups, are groups under multiplication mod n. So this is very interesting. And the last thing that we could look at is something called the Euler-Torsion function. But there's a lot more to go into regarding this. So just to mention it, a group of units, if we take their magnitude, that means the amount of elements in groups. When you're talking about this as a group, of course, its magnitude is more often called the order. So the order of a group of units is equal to the Euler-Torsion function of n, when it's the group of units n. What it means basically is because all the different elements, all the varying elements, all the various elements that are elements of the group of units n go from 1 till n minus 1, where n is this right here. That means that the Euler-Torsion function, when we input n, when we input the value of the index for a particle to create a particular example, look at a particular example of a group of units, and what it talks about is the amount of co-prime numbers that are 1 through n minus 1 in relationship to n. So if we take some number n, how many numbers are co-primed from, how many natural numbers are co-primed to it on the interval 1 through n minus 1. And this is exactly what it says. So this is Euler-Torsion function as an extra to also look at, although we might look at it more closely in the future, look at some proofs perhaps, or go deeper in each of these different topics. There's a lot of things involved in it, because it's all connected with the important topics such as modular arithmetic, integer modulo, n groups, and so on, and n group theory in general.